Hello everyone, this is Firoz Nada. In this video, we will discuss about the further part of the footing. Already we have discussed about the design of footing up to step number 5. Up to step number 5, we discussed about how to find the depth of the footing. We have three criterias by which we have to finalize the depth of the footing. Number 1 is the bending moment, number 2 is one-way shear, and the third one is two-way shear. So whatever depth of the footing that we will provide, it has to satisfy all these three criteria. Okay, so further part will be taken in this video. So in step number 3, you see, we have to find the reinforcement in the x direction as well as in the y direction, and the reinforcement is based on the bending moment. Already we have calculated the bending moment in the x direction. So when we are dealing with the footing, we have to find the reinforcement. This is the plan of the footing that you have. You have to find the reinforcement in the x direction as well as in the y direction. So when you are determining the reinforcement in the x direction, you have to take bending moment in the x direction, MUX. Okay. When you're determining bending moment in the y direction, then it will be MUY. So already we have calculated bending moment in the x direction, and to determine ASTY, we have to find bending moment in the y direction. We will see when we determine ASTY. Okay. Now you see, this is the formula that we have. Everything is given to FCK is the characteristic strength of the concrete depends on grade of concrete. Fy, grade of steel, is given to you. Here you have to substitute the moment, bending moment in the x direction in Newton mm. B, D you already have calculated in the previous video. B, what B we have to take, you see. So when you are determining bending moment, sorry, when you're determining reinforcement in the x direction, this will be your B. So already we know the value of it, 2500 mm. We know the value. But when you're determining AST in the y direction, so L will be the width of the footing. Length of the footing will be the width of the footing when you're determining AST in the y direction. Are you getting? So when you're determining AST in this direction, this will be your B. When you're determining AST in this direction, this will be your B. Just remember this. Okay. Just substitute the value. You will get the value of AST. So this is the value of AST that we are getting after solving the equation. Uh, you see, you have to assume some diameter of the bar. After assuming the diameter of the bar, you have to find the spacing between the bars in terms of center to center distance between the bars. Okay, so how to find that? We have the formula: spacing equal to area of one bar divided by ASTX, whatever AST you have calculated, okay, into width of the footing. So here width of the footing is 2500 mm. Okay, so just after doing this calculation, this is the value that you are getting, but we cannot provide 136.03. We can provide less than this, not more than this. So you see, provide 16 mm diameter bar at the rate 130 mm center to center distance between the bars in the x direction. Okay, so this is the plan of the footing that you have, and you have calculated the reinforcement in the x direction. Okay, the center to center distance between these bars is 130 mm. So now what we have to do? We have to find reinforcement in the y direction. First we have to calculate the reinforcement in the y direction, then we have to assume the diameter of the bar, and after that we have to find the spacing. Reinforcement in the y direction. To determine reinforcement in the y direction, first we have to find the bending moment in the y direction. Okay, so we have to draw the section of the column and the footing, which can be looked from either side, from the left side or from the right side. So how does it will look from the left and the right side? So what dimension of the column will be visible to you? The 300 mm dimension of the column will be visible to you, and the 2500 mm dimension of the footing will be visible to you. Okay, so this is what is visible to you when you look from left side or from the right side. So in this particular case, the length of the column is 2500 mm. The dimension of the column is 300 mm. Okay. Now this footing is subjected to soil pressure. It is subjected to upward pressure, which is denoted by QU. The unit of QU is kilonewton per meter square. What we have to do, we have to convert the unit of QU, which is in kilonewton per meter square, to kilonewton per meter. How can we do that? We can do that by multiplying the lateral dimension of the footing. In this particular case, the lateral dimension of the footing is 400 mm, which is denoted by L. Okay, so when you multiply QU into L, the unit will be kilonewton per meter. Okay, so this will be kilonewton per meter. Now we have to find the bending moment. To find the bending moment, you are required to define the critical section for the bending moment. In case of footing, in case of isolated footing, the critical section for the bending moment is at the face of the column. Okay, so this is just like a cantilever beam. This end is fixed and this is free, and cantilever beam is subjected to UDL over the entire span. So what we have to do, we have to determine this length. What is this length? This length is capital B. What is capital B? Capital B is 2500 mm. Capital B minus small b divided by 2. Small b is 300 mm width of the column. Okay, so you know, when a cantilever beam is subjected to UDL over the entire span, so what is the maximum bending moment formula? The maximum bending moment formula is WL square by 2. So this is our W. QU into L is our W. And what is our L? L is capital B minus small b divided by 2. Okay, so we have to just formulate the bending moment in y direction. Okay, what is our W? W is QU into L. This is our W. Okay, into L. What is our L? B, capital B minus small b divided by 2 square divided by 2. So this is the formula to determine bending moment in the y direction. What we have to do, we just have to substitute the values of all these elements. MUY equal to QU. QU is 225 kilonewton per meter square into 4. 4, the value of L is 4. We have to take in meter bracket. The value of capital B is 2.5 minus small b value is 0.3 divided by 2 whole square. Okay, divided by 2. So MUY value comes to MUY equal to MUY equal to 544.5 kilonewton per meter, kilonewton meter, sorry. Okay, so this is the formula by which we can determine reinforcement in the y direction. So everything is clear to you. FCK, you know FCK, you know FY. We have already calculated moment in the y direction. B we know. D is different here. Okay, so already we have calculated D, but that D is D in the x direction. What D we have to determine? We have to determine the effective depth in the y direction. Okay, so you see, this is the footing in the x direction. Okay, and this is the reinforcement that we have calculated, which is in the x direction. So what D we know, this D we know, and this D is associated with respect to reinforcement in the x direction. D is effective depth. It's the distance from top from this point to the center of the reinforcement. But in the y direction, you have reinforcement here. Okay, so the effective depth in the y direction will be distance from this point to the center of this reinforcement. Okay, so dy. So here we have to take the effective depth in the y direction. So how to find it? dy equal to, so assume that you are providing 16 diameter of the bar in both the direction, in x direction as well as in the y direction. Okay, so already you know dx minus 16 half of this you will get 16 Okay, so dx you know, which is 675 minus 16, dy equal to dy equal to it comes to 659 Now you know all the values, just substitute in this equation. 0.5 into 20 divided by 415, 1 minus under root 1 minus 4.59, mu value is 544.5 into 10 to the power 6. You have to take that in Newton okay, divided by FCK is 20, B is 4000, here B is 4000, okay, into dy. Already we have calculated dy is 659 square into B is 4000 and D is 659. Okay. So AST value comes to, AST in the y direction, it comes to 2327.27 square. Okay, so with respect to the calculation of the reinforcement, with respect to the calculation of the spacing of the reinforcement, in case of rectangular footing, so we have to refer to the guidance given by IS 456-2000 in clause number 34.3.1, page number 65. Okay, so these guidelines is only for the rectangular footing. In case of square footing, you don't have to worry much. Whatever the spacing of the reinforcement you have calculated in the x direction, same amount of spacing shall be provided in the y direction. So we don't have to worry when we are designing a square footing, but we do have some guidelines when we are going for rectangular footing. Okay, so spacing in the longer direction is easy. We already have determined spacing of the reinforcement in the longer direction. The guidelines in the IS 456-2000 is only with respect to the reinforcement or the spacing of the reinforcement in the shorter direction. Okay, so what they say, this is the plan of the footing. So they have divided the it into some zone or some bands, and the central one is called as central band. Okay, central band, and we have to determine the spacing of the reinforcement or different reinforcement for central band and for these two bands. Okay, so what is the what the code says? Reinforcement in central band divided by total reinforcement in the y direction, already we have calculated in the y direction, in the shorter direction, total reinforcement in short direction, means y direction, equal to 2 divided by beta plus 1. What is beta? Beta is the ratio of long side of to the short side of the footing. Beta is ratio of long side to the short side of the footing. Okay, so what is the long side of the footing? 4 meter, and short side of the footing is 2.5 meter. Okay, so we know the total reinforcement in the y direction. We have to determine reinforcement in the central band. Okay, divided by total reinforcement in the y direction, already we have calculated 2327.27 equal to 2 divided by 4 divided by 2.5 plus 1. Reinforcement in the central band equal to 1790.20. Okay, and these are called edge band. These are called edge band. So whatever the reinforcement is remaining, that reinforcement should be provided in the edge band. Okay, so again we have to calculate what will be the reinforcement in the edge band. Reinforcement in the edge band reinforcement in the edge band equal to total reinforcement minus reinforcement in the central band. So you know total reinforcement, and you have calculated reinforcement in the central band. This comes to 537.07 mm square. Okay. One more thing we need to remember here: the dimension of central band is, see, this is 2.5 meter. This will also be 2.5 meter. The central band is something like a square footing. Okay, so the dimension is 2.5 by 2.5 of central band. Now we have to find the spacing in the central band. Okay, for that we have to assume the diameter of the bar. Let's say that we will provide 16 diameter of the bar in the shorter direction, in the y direction, and spacing in the central band equal to pi by 4 into 16 square divided by area of reinforcement in the central band, which is 1790.20 into width of the central band. So you see the dimension of the central band is 2.5 meter by 2.5 meter. Okay, so width of the central band will be 2500. Here we will take in mm. So spacing comes to 280.81. We can provide 280 mm. So providing 16 mm bar at central band at a spacing 280 mm center to center. So this reinforcement is not provided in all of the uh, shorter direction. This reinforcement is only provided in the central band, which means that we also have to find the spacing in the edge band. So what should be the spacing of the reinforcement in the edge band, that we have to calculate. Okay, so spacing in the edge band spacing at the spacing of reinforcement in the edge band equal to pi by 4 into 16 square divided by area of reinforcement in the edge band, which already we have calculated. Okay, into width of the edge band. You see, uh, already we have divided the shorter direction into 3 bands. Okay, so this has been taken by central band. The dimension of the central band is 2500. The total dimension of this is 4000. So what is remaining for the edge band is 4000 minus 2500, which comes to 1500. So width of the edge band is 1500. Okay, so here the spacing is 561.62 mm, which is greater than 300 mm. You see, the spacing in the footing should not be greater than 300 mm. If it is greater than 300 mm, then we have to provide 300 mm as a spacing. Okay, so we got the spacing in the central band, we also got the spacing in the edge band. We can draw the figure, we can draw the reinforcement detail. Okay, So we have calculated reinforcement in the x direction, which is 16 mm at the rate 130 mm center to center. This is the reinforcement in the x direction. In the shorter direction, we have divided into some bands as per IS 456. Okay, so based on that, we have calculated the reinforcement. Okay, so in the central band, the spacing of the reinforcement is 16 mm at the rate 280 mm center to center, and in the edge band, okay, this is where is the edge band. At the edge band, the spacing of the reinforcement is 16 mm at the rate 300 mm center to center. Okay, so after this is the detailing of the reinforcement for the footing, for the rectangular footing. Okay, now one check we have to do here: check for development length. Check for development length. So here we have to see what is the available development length and what is the required development length. So this is the profile or the front view of the footing. This is 4000 and this is 500 mm. Okay, now what we have to do, we have to determine this length. What is this length? This length is available length for DL. Okay, we have to calculate this. This is 4000 minus 500 divided by 2, which comes to 1750 mm. Now required development length is LD equal to 0.87 Fy into 5 divided by 4 into tau BD. Okay, 0.87 Fy, we have taken Hy as the bar, into the diameter of the bar we have provided in the footing is 16 mm, divided by 4 into tau BD. Tau BD for Fe415 is 1.2. It comes to 1203 mm. So available development length is more than the required development length, hence the check for development length is okay, and hence the design is okay. So I think you have enjoyed the learning. If you have any question, you can ask in the comment box. Thank you very much. Thank you for watching this video.